his work. And tomorrow, actually tomorrow, Wednesday, and Thursday, they all begin at 1 o'clock. And tomorrow is...
That's next week, isn't it, Kevin?
Huh?
That's next week, isn't it?
Oh, yeah, sorry. It's next week, I'm sorry, next Tuesday. So this week is only today, and then the next Tuesday, Wednesday, and Thursday all begin at 1 o'clock. It's here. Today's presentation is by Ming. It's scheduled earlier because of his schedule. He actually will leave or finish years and leave the country just tomorrow. But he is also will be presenting this paper in July, I think 6th or 7th in France. So today's dry run, I request you to be very critical. So that your feedback is very important to make the presentations better. So I will give all the rest of time to Ming, and then Ming will explain what the research is about.
Okay, yeah. Thanks. First, I need to confess, I'm nervous. And this is a paper that we have been working on since last July, and they were done in almost near 1 year. And we are near the end of this paper, trying to get it published soon. As the name suggests, it is doing some hypothesis testing in the paradigm model with spatial dependent variable as well as a spatial correlated error component. And first, I would like to give you knowledge about what is a spatial econometrics. For example, we have a typical linear model without spatial effects, which we are very familiar with. And we can also have a linear model with spatial effect, where we can see the dependent variable y here is a vector, and the dependent variable is spatially correlated, which is captured by this spatial weight matrix, as well as the lambda here, which is a parameter used to represent the magnitude or extent of the spatial dependence. And by the same idea, we can have this spatial dependence in this error term, which is captured by the spatial weight matrix, as well as the parameter rho here. So the idea here is that the dependent variable of one unit is going to depend on the dependent variable of its comprehensive labor, and the same case as in the error term here. Let's see what kind of earlier researches they have done. In 2003, Bertagli, they have done this random effect, but in their paper, they included this spatial correlated error, but there's no spatial correlated lag. In 2007, this Capua and Clegian also random effects, spatial correlated error, and there's no spatial correlated lag. In these two papers, there are some slight difference in their spatial correlated error term, but that is not so important. So, and this paper, Bertagli and his student also used random effect, but they excluded the spatial correlated error, and at the same time, they included the spatial correlated lag. On the other hand, Berra and Jung, in their paper, this 1993 paper, they proposed a general theorem about this robust or so-called locally adjusted Lagrangian multiplier test to correct for some local specification. Later on, they published another paper in Journal of Econometrics. Basically, that is the application of the early principle, in which they extended the result in the Bush and Bacon 1980. The contribution of our paper is that we also adopted a random effect model. So this is where we're squeezing. We included a spatial correlated error term as well as a spatial correlated lag. And then we constructed this traditional Lagrangian multiplier test, as well as we applied the Berra and Jung's principle to construct the locally adjusted or the so-called robust Lagrangian multiplier test. So this is our model specification. As you can see that because this is parallel data model, and for the spatial equal matrix, in order to express this spatial dependence, we need to arrange the data according to t first, not n first, not the traditional n first. So for each t period, we have this y is dependent depends on some exogenous variable as well as itself here, its comprehensive label. And for the error term, it can be decomposed into two parts. Here, this is also used to express this spatial dependence. And this term here, the E, is decomposed into two parts. One is a U, which is a random effect, and the V here is an innovation. We assume this is a normal distribution, and the variables they are defined like this. Here, this term here is denoted is used to denote the Kronecker product. So we can stack them together to get this stacked form, which is
Why do you have the same weighting matrix for both the spatial lag and also the spatial correlation?
Yeah, generally they do not have to be the same, but here is just for the ease of implementation. Yeah, thank you. So we can get a stack form here right now. The process, I want to say a little bit about the process, because the general statement says, okay, for adding value, first we have to generate the data, the X matrix, which after we generated data, this is fixed. And then we can specify adding value of beta, lambda, rho, and the sigma u squared, sigma v squared. And the general statement says, for any given value of this parameter, the Lagrangian multiplier test statistics will follow a certain distribution asymptotically. So in our statistical experiment, we can just specify, we can control for the process. So each time we specify the value of lambda, specify the value of rho, and specify the sigma u, sigma v squared, as well as beta here. So when they are fixed, every time we can use a random generator to generate a u here and generate a v here, then we can get e here, and using this formula we can get epsilon. Using this formula we can get y. So y is basically essentially a random vector in turn, which comes from the random vector of u and v. So in this case we can write down the log-factor function of this random vector y, which will look like this. Essentially we can see it is kind of complicated, but essentially it is just a function of sigma u squared, sigma v squared, and AB is defined like this. So basically they are just a matrix in terms of rho and lambda. At the same time, it is also a function of the beta here, and this symbol they are defined like this. So in general, a statement of a Lagrangian multiplier test is saying that, okay, we have this log-factor function for any given x and y. We want to find the parameter vector which can maximize this log-factor function. So if the data of the data of random variable y is generated according to some law model, or the data generator is specified under null hypothesis, then we can construct this test statistics using this formula. And then if the data is generated by the law model, then our conclusion is that this term will follow a chi-square distribution asymptotically with the degree of freedom is alpha. Alpha is the constraint, number of constraints in this constraint maximization process. The first term is a score vector evaluated under null hypothesis and evaluated at the restricted estimator. The middle part it is information matrix, also under null and evaluated at the restricted estimator. This guy is just a column of the column form of this score vector. And the general statement of robust test, that is also called the Barra and Young's principle, is that if we have a model which can be captured by this log-factor function in terms of this parameter vector theta here, but we can decompose it to three parts, to the gamma, psi, phi, they can all be the vector. And the phi here is a parameter vector that is involved in this hypothesis. And phi is a nuisance parameter which we have some pre-knowledge about. And gamma here is a parameter vector we needs to be estimated from the restricted system of equations. So, for example, if we have this null hypothesis, rho and equals lambda equals 0, and then we assume the sigma u squared equal to 0, which means we have very strong confidence. Okay, the model should be a random, there should be a polar model instead of a random effect model. And then hy here is our y, which means at least one of them is not equal to 0, and at the same time we assume the same thing. So in this case, the parameter vector involved in the null hypothesis is just rho and lambda, and the phi here is the assuming part, which is a nuisance parameter. That's here it is sigma u squared, and the gamma here is beta and sigma v squared, which we have to estimate them. But there is one problem with this marginal AM test. For the what is the definition of the marginal AM test? I will explain in next slide. We have this null hypothesis, and we can construct the traditional Lagrangian multiplier test under this hypothesis. So if the real data generator is just this one, it will be fine. The Lagrangian multiplier test will perform very good. But if the data generating process is XS here, although the null part it is the of C equals to C naught, but the assuming part it is not the same as here. The assuming part, which means the phi will deviate from this pre-specified value, our hypothesized value phi naught. So there will be a problem. In this case, if the real data generator is under this guy here, then we use the same. We use a marginal AM test. So the marginal AM test constructed under this hypothesis will follow a non-centralized chi-square distribution, which this is not good because it's going to distort our asymptotic size, which will lead us to reject the null very often. Even if this is the null part, we compare here and here, the null hypothesis part is just the same, right? This is what we're interested in. So in this case, Berra and Newton's principle should be used to correct for this problem. And here, this is general form to construct a robust test. And I'm not going to go to these details about this formula. Basically, essentially, it is used to adjust the expectation and the variance of these two test statistics. Here, this is one part of the information matrix. Here is another part. There is one advantage, as I have said. The robust test here, the advantage is that even if the real data generator is from here, which means there is no co-deviation of the phi from the phi naught, the robust test still, in this case, we are supposed to accept the hypothesis because our hypothesis is just C equals to C naught. In this case, we are supposed to accept it. So the robust test in this case will follow a centralized chi-square. So in this case, we can regain this valid asymptotic size. This is the advantage. For the disadvantage is that maybe the real data generator is under this term here. But in that case, we can use a robust test, or we can use this marginal test. If we use in this case, we are supposed to use marginal test, which is preferably. But if we use a robust test, there will be a problem. That is, if this is true, the robust test will be less powerful than the marginal test when the C deviates from C naught. And there is a general property is that the joint test of these two parameter vector will be equal to the marginal test, that is, we are testing the C, assuming phi, plus the robust test of phi. And it will also be equal to the marginal test when we are testing the phi and assuming the C. plus this robust test of with respect to the C here. One attention here is that this statement is only asymptotically true when there is just a local deviation of the phi from the phi naught. For example, if the hypothesized value of phi naught is 0, and then this statement will only be true when the phi, maybe it is from 0 to 0.5 or something, but it cannot be very far away from 0. Otherwise, this general statement will not be true. Okay, here is a roadmap of our test statistics. We have 3 parameters to the parameter of interest. That is a rho, which is a spatial arrow. The lambda is a spatial net, and the sigma u squared is about a random effect. First of all, we have this joint test. We have one joint test. That is 3 of them are just not our 0. And then we have this marginal test. We have 6 of them. We have one-dimensional marginal. 3 of them will have 2-dimensional marginal. The format here is like that. The marginal means we have to assume something, which means we have some kind of pre-knowledge, which makes us confident to assume something. Here we can assume this phi equals phi naught. Under that, we want to test whether C is equal to C naught or not. One-dimensional marginal test means the C here there is only one parameter, and 2-dimensional marginal test means in the null here there are 2 parameters. So essentially the C here is a vector. There are 2 parameters in there, and we also have 6 conditional tests: one-dimensional conditional, 2-dimensional conditional. The format is that we don't know whether this is true or not. But if we are not confident, so maybe we should not use the LM test constructed under that. So maybe we should allow it for the deviation of the phi from phi naught. Under that, we can still test for the phi and then equals to phi naught C equals to C naught or not. We also have some one-dimensional semi-marginal tests. We have 6 of them. In this case, we assume one part and we allow for another part. Essentially, it is still based on different knowledge about it. There is, at the same time, here I want to address that. For every marginal test, because we need to assume some parameter is equal to some specified specific value, but maybe that is not true. And if we use a conditional test, we need to use this maximum negative estimation process, which sometimes will be very cumbersome and maybe even impossible. So in that case, robust test is also a good choice. So for every marginal test, we also constructed a robust test to guard against this potential deviation of Newton's parameter from this specified value. Here we go. This is the first test statistics. The joint. The null here is, okay, 3 of them are equal to 0. With this alternative is, at least one of them is not equal to 0. The test statistics looks like that. I cannot go into details about it. And this variables that are defined like that. Here, this is W prime, and the omega A is defined like this. But in this case, because our null model is just a pooled model, so it's a traditional pooled model, pooled parallel model. So here we just need to use basically OS, because this is essentially the same as the maximum negative estimator. So the statement here is that because in our data generator we can specify different values. So the statement here is that if under the null hypothesis, which means in our data generator we specify 3 of them to be 0. In that case, when we do the random number generation for many times, each time we can get a number for this one. So this is a random number. In that case, the term here will follow a chi-square of centralized chi-square of degree of freedom to be 3, because we have 3 constraints here. We also have this.
When you say asymptotically distributed, what is going to infinity here? Is it Is it N or is it T? Are you working with a short diameter or a long diameter?
Here in our sample size, we have two sample size. One sample size is larger, another is smaller, but one is larger than the other one. T is larger than the other one, and N is also larger than the other one. So here, I think it is still N, right? But T is also okay.
I understand that you're running some Monte Carlo experiments, is that right?
Yeah,
And then that's how you get a distribution of your statistic,
yeah,
right?
yeah.
So what is going to infinity in these experiments?
In the experiment, it is still finite sample, but the performance is good.
Right, but
Yeah.
what are you increasing as you run these Monte Carlo experiments?
We have two sample size. One is N equal to 25 and T equal to 3, and another sample size N equal to 49, T equal to 7. So both of them increase. We did not just control for T and then increase it. And
You have two sample sizes?
yeah, we have two sample size.
And you don't see what happens when you increase sample size?
I see what happens when you increase sample size. It's per count afterwards.
Okay.
And we also have this one-dimensional marginal test. Basically, because we have three parameters for the one-dimensional, we have respect of one of them, and we assume the other two of them. So we can just make the different combinations. First row, and then lambda, and then the sigma u squared. We just assume the remaining parameter vector to be 0. And in each case, we can construct the robust test. For example, here, this is robust test corresponding to this hypothesis here. It will look like this. And the reason here is that if in the data generator, if the lambda and the sigma u squared deviate from 0, then the marginal test will produce some problem. So in this case, we also use this robust test to guard against this local deviation. And this is a two-dimensional marginal hypothesis, and their corresponding robust test, you see, it is the different combination. First row and lambda, we assume this sigma u squared. This is the whole model. And the second one, we combine the row and sigma u squared. We assume the lambda equal to 0, which means we are very confident that there is no spatial lag-dependent variable effects. And here, we are confident, okay, in the error term, there is no spatial correlation, but we are not sure whether there is random effect or whether there is spatial lag-dependent variable effect or not. In all of these cases, because we combine the null part, the null hypothesis part as well as the assuming part, is reduced to the traditional pooled parent model. So all of these cases, this estimator or the U hat here, the Y hat, fit value U hat is the estimation strategy here are over OS.
Ming?
Yeah.
When you call these robust, that's where you assume the same hypothesis, but you don't assume the nuisance parameters necessarily equal to 0.
Yeah.
Is that right?
Yeah. And we have this two-dimensional conditional test, two-dimensional row and lambda. But here, maybe we are not sure whether this is random effect model or whether it is real model. So in we can construct the corresponding conditional test here. The formula is kind of messy, and in this case, all of them, they are maximum likelihood estimator because we have estimated sigma u squared here. This is also two-dimensional conditional test. We can here in this case we allow the lambda to be not to be equal to 0. But yeah, there's still some difficulties, especially in the Gaussian implementation, because for the maximum likelihood estimation, it is sometimes it is even impossible to find a solution. Also, two-dimensional conditional test. This is a one-dimensional condition test. First we test for row, and then we allow for the lambda not equal to 0, and sigma u we allow it to be greater than 0. And two more one-dimensional there are more, 6 more. This is called one-dimensional semi-marginal corresponding robust test. We still need to work on find a good name for this because the doctor is not happy about this. Here, you can see we assume one part. We assume this is for model, and we allow. We think we're pretty sure. We are very confident there is this spatial correlation in the arrow, and then we want to test it for the lambda. We get this formula here, and also there is this robust test corresponding to this guy here. As you can see here, in this case, the semi-marginal test is just the same as this robust test. The reason for, I think here in this case, it is also the same, and the same as here. The reason for the marginal test to be equal to the robust test is that we can go back a few slides to see. You see, in the construction of the robust test, basically this whole term is used to adjust for the expectation, and this whole term is used to adjust for the variance. So we can see that this term here is the same as this term if this term is equal to 0. So the same as this term. And then the whole term here will be 0. This term will also be 0. So in that case, the term here the robust term on the left will be exactly the same as this score term in the traditional Lagrange multiplier test, the same as this information matrix here. So this is a very easy condition to check in practice to see if this term here is 0 or not. If it is 0, then the marginal test will just be the same as the robust test, which means that even if there is some local deviation of the nuisance parameter from the specified value, the marginal test will still produce a valid asymptotic size. Yeah, this slide is also the continuation of our one-dimensional semi-marginal and the corresponding robust test. Let's go to the Monte Carlo simulation. In this experiment, we can specify different value and we can have total control of this simulation. Our data generation process is according to this formula, or we can see it as a random vector transformation like machine or something. We specify the value of alpha, specify the value of beta, and x is pre-generated according to this formula. And for the sigma u square and sigma v square, we can control. We specify add them up together equal to 1. This is not of great importance because for the general statement, it is valid for any value of the sigma u square and sigma v square. And for the eta here, yeah, we make the eta to take 0.2, 0.5, and 0.8, just a different combination of the sigma u square and sigma v square. For the rho and lambda, it runs from negative 0.9 to 0.9 with an increment of 0.1, same as the lambda here. The absolute value of the rho and lambda are smaller than 1, just in order to keep the system stable. And for the spatial weights matrix, we use a Queen and Rook and Queen criteria. For the sample size, we have two, first one and second one. So in this case, for the different combination, we end up with 5,576 experiment. And for each experiment, we can get this Lagrange multiplier, which multiplier test statistics, which is essentially a random variable. So we do the 1,000 replication for each experiment. And we specify the nominal size to be 0.05. This is the first result of the joint test. Remember, the null hypothesis is all of them are equal to 0. But here, we need to use, we cannot see it very clearly, but this is a frequency of rejection. First, we specify the critical value, and we do 1,000 replication. Each time we can get a value, and then we can see the value goes beyond the critical value or not. If it goes beyond the critical value, we reject it. So here, the z-axis is frequency of rejection, but we have 3 other parameters here. So each time I can only plot I need to fix one parameter and plot the power function with respect to these 2 parameters here. So in this case, we can say the sigma u squared is equal to 0. And then if the rho and the lambda equal or equal to 0, which is represented by the point in the middle, in that case, the Lagrange multiplier test statistic should be a centralized chi-square of degree of freedom with degree of freedom to be 3. So in that case, we are supposed to accept it. We are supposed to accept it. So the smaller the frequency of rejection is, the better. But if there is this deviation of the rho and lambda from 0, we can say in all of these directions, the frequency of rejection will increase. As we can see here, the frequency of rejection will increase very rapidly. So, because in that case we are supposed to reject it, so the power function climbs very rapidly, which is desirable. And in this figure, also a joint test, but the first one, the sigma u squared is equal to 0. We can have this point which represents the size. But the second one, the sigma u squared is equal to 0.2. So in this case, we are supposed to reject it no matter what is the value of rho and lambda. So as we can see that the frequency of rejection is almost 1, although in the middle there are some points. The frequency of rejection is 0.9 or even more than 0.9. As also we can increase the sigma u squared to 0.5 and to 0.6. So we can say the frequency of rejection, they are all uniformly 1, which is very good. Here, this is power function of one-dimensional modular test, assuming this poor model. Our null hypothesis, first we assume this is poor model, and then we assume there's no spatial lag-dependent variable effect. We want to test whether there is this spatial correlation in the error term or not. And the power function looks like this, because the x-axis is rho, and when the rho deviates from 0, here in the point in the middle, we're supposed to accept it because the rho is equal to 0, which is a null hypothesis. But when it deviates, we are supposed to reject it, as we can see that the power function increases. Here I plotted in the root case as well as in the green case for the 2 samples. As we can see that the power function performs increase more rapidly when the sample size increase. For example, for the root, for the 25 times 3, the power function is a solid line. But for the larger sample size, it is the line in the inside, the most inside line, which it climbs very rapidly. This is desired. Also, we can have here, we can test for the lambda, also one-dimensional modular test, and to plot the power function in different cases. This is the power function of the random effect. First, we test for rho, and because this is random effect, we need to specify the value of sigma u squared not equal to 0. So we specify sigma u squared equal to 0.2 and 0.5, 0.8. But in this case, I just plotted the case where the sigma u and sigma u they are equal to 0.5. And here we can also test for the lambda, and it's the same power, the power function of the same pattern. In this slide, I want to compare for the size and the size for the marginal and robust test. Because just now I have talked about the advantage of the robust test, which means if there is this local deviation of the Lewis parameter, then in that case, robust test, the marginal test will tend to reject the null hypothesis to open, even though the null hypothesis is right. But the robust test it will not reject the null very often, so which is desired. So in this case, we can see that the null hypothesis is lambda equal to 0, assuming these two are equal to 0. And in this plot, please we notice that the x-axis is rho. It is not lambda. If it is lambda and then lambda deviates from 0, the power function is supposed to increase very rapidly. But actually here it is not. It is rho, which means that for all of this point here, rho lambda is equal to 0. So that in the real data generator which we can control, this is true. We're supposed to accept it, or the frequency of rejection is supposed to be very low. But in this case, for the marginal, which is a solid line, it increases very rapidly. This is not desired because in this case we're supposed to accept it instead of reject it. But for the robust test, you see, it will increase but very slowly. And because I have said the robust test general statement is only valid in a very in a small neighborhood in the local deviation. So here we can see from maybe negative 0.5 to 0.5, the frequency of rejection is very small, which is consistent with our data generator. And in this slide, we can do a comparison of power for the marginal and the robust test. Here, this is essentially the disadvantage of the robust test. If the null hypothesis is like this, and if this is really true, this is true. But if this is not true, we can see it from here, the lambda can deviate from 0, right? So we're supposed to reject it. We're supposed to reject it. In this case, for the marginal test, the power function increases very rapidly. And for the robust test, it also increases, but not so much. But in this case, the power function is increasing very rapidly is desired because the lambda is deviating from the 0, from the null hypothesis. We are supposed to reject it, right? So the frequency of rejection is supposed to be high. This is also the comparison of size for the two tests, but this is for the random effect. And this is the comparison of the power for the two tests, also for the random effect. They follow the same pattern, but although here in this case, it seems like the cost of the robust test is not so much because the power function also increases rapidly, although it is not as rapid as the marginal test.
Shouldn't those pictures be symmetric?
No, not necessarily, but I don't know why. Yeah.
The negative spatial response and positive spatial response is not necessarily the same.
Yeah. Here, this is the power function for this test statistics. The null hypothesis is rho equals to lambda equals to 0, and we assume the full model. Here, this is the case for the small sample size, and this is the case for the large sample size. As we can see that from in the middle part, the same. When the rho and lambda are equal to 0, in this case, we're supposed to accept it. So the frequency of rejection is very low. And when the rho and lambda deviate from the 0, so the power function will increase. The frequency of rejection will increase until 1. And for larger sample size, of course, the performance is better. Right? And this is the power function. In this slide, we assume this is a norm model. And in this slide, we assume this is a random effect model. So that I also just plotted this case, but in our experiment, we used sigma u squared equals to 0.2, 0.5, and 0.8. We can also see the same pattern here. And some future research suggestions. First of all, in the innovation term, we can allow, right now it is still, we'll still assume this homologous elasticity, but it can be, the homologous elasticity can be allowed. Also, we can allow for this different magnitude of spatial population in the error term, because this is our data generator, right? Here, just as per Gap just like I said just now, we can allow for the two spatial weight matrix to be different. That is another generalization. But here we can see this is our model. So for the innovation, we can have a spatial effect. For the individual random effect, we can also have it spatially sphered over. But the strengths of these two are the same, right? So, but it does not need to be the case. So we can generalize this specification by allowing these two parameters not to be the same. This is some future research suggestions. Questions?
Would it be possible to have a sequential test? Because you were showing that if the hypothesis on the nuisance parameters is true, you have a much more powerful test.
Yeah.
More powerful than a robust test, which is not necessarily true. But is there any way that you can pre-test for whether the nuisance parameter is zero or not,
is true or not,
and then retest on the basis of that, and figure out the whether that improves your power or not?
Yeah, but we still, in that case, we need to use a conditional test. For example, if we don't know if this is true or not, right?
Right.
So first we want to test it.
With a robust test.
Yeah, we want to test it, but we don't know this is true or not, right? We don't know if lambda is equal to 0 or not. So we can go back to the conditional test. Should be two-dimensional. Yeah, we can go back to this conditional test to see if they are 0 or not. But we, at the same time, we allow lambda to be 0. Does not need to be 0.
Right.
But yeah, there is still some difficulty we need to solve because the maximum likelihood estimation is not so easy. Yeah.
That'll get more complex, but you might have a better power than.
Yeah. We will implement this. Yeah. And more.
Yeah, I have a couple of questions and comments. The first question is, so why did you go for the Lagrange multiplier test? Did you rule out other possible tests? Why is this more fits better spatial?
You mean, for example, I can go with wall test or non-canonical ratio test, right?
Yeah.
Because most of them are pre-test, and Lagrange multiplier test we are just required to estimate the null model, which is simpler, right? For the wall test, we need to estimate the alternative model. In that case, definitely we need to use a maximum likelihood estimation strategy. But yeah, but it has been proved that theoretically, in the asymptotically, the wall test and Lagrange multiplier test, as well as the non-canonical ratio test, they are just the same, right?
It has been proved under spatial correlation?
I think it has been generally proved, right?
Not so
Eventual.
Well, the advantage of using an LN test is you estimate it with strict model, or as just fine. If you want to do the likelihood ratio test, then you have to estimate both models, with strict and unrestricted. And unrestricted model is more typical. Yes.
Yeah, as long as it
it's
involves.
in the interest of simplicity.
Yeah.
And then when you're beginning to construct the model, pre-test, you run the pre-test. Pre-test is you don't estimate any specified full model, right? You just the very restricted OS model. So you just take that, then you run the marginal test, and robust test. You get some ideas of constructing the unrestricted model, and then you can apply the conditional test to do the post-testing.
Yeah, to do kind of the confirmation whether the model is right or not. Yeah, but yeah, for the module test and robust test, they are pre-test, kind of we use it to do a model search, to search for the potential right model, but when we study, we have some idea about it, and then we can use this conditional test to confirm whether the knowledge is right.
I'm still worried about the asymptotics because I don't know a lot about short panels, but I do know that when you let your periods go to infinity, when you have a lot of periods, you have to worry about stuff like stationary, things like that. Whereas when your asymptotics is done on n, the cross-section dimension, then you don't have to worry about any of that, and that's usually the asymptotic results you see in your, at least the early literature. So when you say that you can either increase n or t there, I don't really understand.
Yeah, for the t, I'm not so confident. If we increase, I think not. If we increase the t, the estimator will not be consistent, right?
There's a asymptotic theory for panel data, and which allow n to go to infinity, but t is finite, or the other way around, or both n and t go to infinity. And I think this paper, the asymptotic theories of the statistics require you to have theoretical assumptions satisfied, and then you prove the distribution to be asymptotically normal or chi-square.
Yeah, but they're different. The assumptions are different depending on whether you let n or t go to infinity.
Yeah. And I think this paper it's not proving that asymptotic. It's not part of asymptotic theories, and it just assume it just formally, of course, you need a proof of the asymptotic theory, but you just assuming the asymptotic theory is correct from previous studies.
Yeah, this is kind of like a empirical approach.
And all these presentations is T-first representations, right? And then and actually it's restricted by the W matrix there. So the theoretical extensions is the T going to infinities, and you know.
Mean t?
Yeah.
I think we just
Let me make my comment, and that is that it's a word of advice regarding the presentation. I understand you're going to present this to statisticians or econometricians, right? But you have to adjust your presentation to your audience. And especially all these equations and expressions, if you're not going to explain them, I don't see any point in having them in the slides. Just show your final results and then give interpretation and try to discuss the results you obtain. Because I'm pretty sure you lost many people here with that.
yeah, I'm also positive.
It's probably one of the first times you present, so you will learn as you go along.
Yeah, I'm also kind of confused whether to put this formula there or not. You can just interpret that just one kind of show.
Your sample sizes are pretty small, and so I was just wondering what's the implications and like the feasibility of this test as sample size increases, and also if you're not using contiguity matrices, that you're using spatial weight matrices defined by distance functions in large samples, like how feasible is this test?
We use a Wu and Queen criteria.
Yeah.
What is that? Basically there are two different criteria. We have this, if we have this 9 units a day, it's like the Wu criteria. So labor of 5 is just 2, 4, 6, and 8. If the Queen criteria, so all of them will be his neighbor, even if like 1 and 2, 1 and 4, 1 and 5, there is sort of 1 point where they're adjacent. So we use those 2 criteria. But yeah, the same case can be applied for the geographical like contiguity matrix, or the geographical distance. Yeah.
Yeah, I mean, you can also define it through a distance decay
But
function, like a
Yeah.
spatial,
yeah, the distance function we can also define that. And more.
Well, I just remember from last term that these tests are much more difficult once the sample size
Yes.
dramatically increases, and
Yeah.
if you're using distance functions, and the
Yeah,
matrices
this-
aren't scarce.
Yeah, we can create matrices here are pretty relatively simple. If we use real data, use distance function, it will cause some difficulty. And especially when the sample size goes to very large panel, it will involve the inverse of a very big matrix. So yeah, it might create some problem.
Yeah.
And also the theoretical presentation typically will have the asymptotic theory, is mathematically proved that shown to be true. And then all these multi-color simulation is trying to verify the small sample count. Because once the sample go to large, that theory kick in.
Yeah, the theory.
But when the sample size is small, you don't know. So that's the purpose of simulation. They restrict to the smaller sample size to see they still perform reasonably well. So that's why you use 2 cases, 40, 49, 25.
But it might also theoretically that should be true in the large sample. In the asymptotic, but it might be case for the very large sample cannot find a solution, right? It might happen.
No, for the large sample you can still, because you only do the OS anyway.
Yeah.
So it just take a little bit of time.
Yeah. All right.
I think when Ming run how many experiments? 5,000?
We run 1,000, 2,000. We also tried 5,000.
No. Total numbers of experiments for your presentations.
Yeah, 5,576.
Yeah. How many days you need it?
I don't know. Yeah, it was very long. I mean, generally for each, because we don't run. Sometimes we specify the value, so there are 19. There are also another 19, and then for here we have 3 combinations. So each time we have like 16. No, 19 for this is 19 and 19, and then here it is 3. So we have I don't know, but yeah, every time maybe it's
So this is only the larger size is only 49 times 7. If you are run like 200 times 100, they're not going to be very time consuming.
Yeah.
Although it's all the OS, but still.
Yeah, because we have to do so many replication. I think I tried to do the sample size with n equals to 121 and the t equals to 10 or 20, and then I roughly calculated it's going to take like 11 days, so I cannot do it. Yeah. And more.
And also that's another reason is stick on the marginal and the robust test instead of conditional test, because one maximum likelihood probably improvement to 200 or less. So that's if you run all these experiments, you need I think you need 6 months to do it.
But that is for the statistical experiment. But in the real case, we just have 1 time, right? We don't have to do 1,000 replication, which we will have to control. So, if there is no more question, I would like to say a few words to express my gratitude because I'm learning tomorrow. First of all, I would like to thank Dr. Ming for giving me the chance to work with him, and especially I want to thank you for not pushing me, because which makes me struggle a lot at the beginning. But in retrospect, I kind of feel like maybe you did this on purpose to make me struggle. But this transformed me from the track of a student to a track of author or researcher, which is very beneficial for me. And I also would like to thank Dr. Gao and Dr. Rivera for your support when I was applying for the PhD program, and as well as my cohort, super friendly and super competitive cohort, which you guys inspire me a lot. And I appreciate your spirit of hard working